Well, it's my great pleasure to introduce Sandy to everyone who already knows him. Sandy Zabell, who is teaches both in math and in statistics at Northwestern, but the things he does that I am, of course, most interested in, and probably most of this group also is his work on the history of statistics. I mean, he's one of the leaders in that field, and I'm glad he's still at it. And we look forward to seeing what he will tell us today about RA Fisher. Sandy.
Okay, so let me just get my slides set up. And okay, so I can share the screen, I trust.
Yeah, I think you can.
Okay, good. So I'll share the screen. And then so does everybody see this first slide, which says Fisher, Bayes, and predictive inference? Is this visible to everybody?
Oh, yeah.
No?
Yes.
Yes.
Yes, now it appears.
Okay, so today I'm going to talk about Fisher, Bayes, and predictive inference. So Fisher refers to the great R.A. Fisher of the last century, one of the greatest, if not the greatest, statisticians of all time. Bayes refers to the Reverend Thomas Bayes. Now, during his lifetime, Fisher was, Fisher is largely regarded as a sort of the antithesis of Bayes, and was highly critical of people who used Bayesian inference. But if we look at his last book and trace his career up to then, things seem a somewhat different picture emerges. And so especially when you talk about predictive inference. So that's going to be the topic of my talk today. So this is since this is supposed to be foundations, and I think foundations are often best understood or an important aspect of understanding the foundations of our field, I think, should be grounded in history, because where we are now is conditioned by how we got there. So this talk is going to be largely historical in nature and philosophical, but I'll also throw out a few teasers in terms of some mathematical details. Okay, so who was R.A. Fisher? Ronald Elmer Fisher. So he was a towering figure of 20th century statistics. He wrote a number of books, but his best known books are, first of all, Statistical Methods for Research Workers, which was written in 1925. So this is after he'd started developing most of his small sample exact methods. And so this was a very successful book because he told people how to do various tests of significance and other techniques, but he ruthlessly expunged essentially all the mathematical details, but he summarized in a very understandable way how to actually do things. So this book was widely used, if not always understood. In fact, I believe George Barnard writes somewhere that he got this book from Fisher at some point when he asked Fisher what he should read to understand about statistics. And he says about 20 years later, he thought he actually had read through and more or less understood the book. Another book, another book is 1930, he wrote The Genetical Theory of Natural Selection. So if you look at Fisher's collected papers, you'll see that in every year, about half the papers he writes are in statistics and half in genetics. And I'm told that, you could talk to statisticians who might be very surprised to learn that he did anything in population genetics, but also you could talk to population geneticists who might have been surprised to find out that he did great work in statistics. And so this was his a masterpiece which summarized his work up to that point. Then in 1935, he wrote a book on the design of experiments. So his first long-time day job was at Rothamsted, which was an agricultural experimental station. And it was a wonderful place for him because people would constantly come in with these real world problems with tons of data, and then he would think up new methods to deal with them. And so he invented, if you like, the field of the design of experiments and wrote a book on it in 1935, which was also greatly successful. And then now he's written a few other books which are not in the same league, but he also wrote a book in 1956 called Statistical Methods and Scientific Inference. And this doesn't really have the same edge that the other books did. Fisher was sort of dismayed at the beginning of the 1950s to find out to what extent in the United States the Neyman and Pearson type techniques had taken over. And so he started waging battle against Neyman in various journals. And then this book was an attempt to summarize as best he could his philosophy of statistics. So it engages in a certain amount of controversy, not a certain amount, a lot of controversy. It doesn't have the same plethora of new and exciting novel results, but still it's extremely interesting to read. So, and then, now he's ordinarily thought of as a staunch opponent of Bayesian methods, but this last book actually views Bayes quite favorably. So contrary to the usual way he's viewed, and so part of my talk today will be to understand what happened. Why is that the case? And here's a posed picture of him. So back in the good old days when you used desk calculators rather than computers or these electronic gadgets, this was a calculator, and he's posed working away at one. Okay, so what was Fisher's initial view on inverse probability in the 1920s? Very critical. So he says the attempt made by Bayes, upon which the determination of inverse probability rests, admittedly depended upon an arbitrary assumption, so that the whole method has been widely discredited. So this is a paper he wrote in 1921. So if you read him in 1921, he's saying, nobody believes this stuff anymore. And then in a paper written the next year, he says, inverse probability, which like an impenetrable jungle arrests progress towards precision of statistical concepts. So he relished controversy and wrote in it's an interesting style when you get used to it. It's not, it's a little labored, but there's a sort of crafted elegance to it at the same time. So obviously these are and these are papers in which some of his pioneering work on statistics was being put forward. So he's obviously a critic of Bayes. But this was already a viewpoint change, because he says, I made myself say that I learned inverse probability at school as an integral part of the subject. And for some years, no reason to question its validity. And then in another paper, he says, I must indeed plead guilty in my original statement of the method of maximum likelihood, which was the paper he wrote, his first paper actually in 1912. He says he has to plead guilty to having based my argument upon the principle of inverse probability. In the same paper, it is true, I emphasize the fact that such inverse probabilities were relative only. So in 1912, he had just graduated from Cambridge. So he was just a fresh BA. And he's saying, at this point in my early stages of my career, I didn't see any reason to question the received wisdom. But you can see that by a decade later, in 1921, 1922, he's taken a completely different viewpoint. It's not that he no longer holds those views, but he's harshly critical. Now he reasons that uniform priors are not invariant. Okay, so suppose you take, oops, sorry. Says, suppose you do the transformation and set sine theta to be 2p minus 1. So theta is actually the
asymptotic limit of an unstable connection. I hope we can get a more stable one.
Up as soon as it happens. I don't know why the internet is like that, but okay, so we were at this slide. And so one of Fisher's points was that if you took a uniform prior on P, which is very common, but if you do this one-to-one transformation between P and theta, they're equivalent formulations in effect of the same thing, and yet the uniform on P translates into a very non-uniform distribution on theta. And so his point is that this formulation of ignorance is scale dependent. And so therefore, what's the argument? Yes, I'm uniform for P, but I'm not uniform for theta. And what's the justification? So unless you want to say somehow that P is the right scale, there's no real justification for being uniform, because you're tying yourself to a particular scale, and that's not in part of the ignorance assumption, right? So this was one of a number of arguments that he advanced. Now, if you read his book, he had some, he was familiar with a book by Van Gries, and he wasn't the first to raise this objection. Actually, Johannes van Gries, who wrote a really quite impressive book called The Principles of the Calculus of Probabilities in 1886, Van Gries gives an example where he says, suppose you take the specific weight, call that sigma, of a substance, but you also look at omega, the reciprocal of sigma, which is the specific volume, then he says a uniform prior for one is not uniform for the other. And so he says the probability assumption is therefore undetermined, right? So, and in some ways, this is a nicer example than Fisher's, because specific weight and specific volume both have physical significance, but there's no real argument for saying, what's the preferred scale on which to assume uniformity. And then also in the, if you go and look, Van Gries goes on to say that, that a variety of other examples are easily given. And so he says, for example, if you look at a pendulum and you look at the frequency or period and so on, you have the same kind of phenomenon, that something that's one quantity determining the motion. If it's uniform, well, you could just as well look at a different and have the same thing. So this is certainly a strong argument against uniform. It's making it clear that in some sense uniformity must be making some kind of implicit assumption about scale. And here's a picture of the great Van Gries, a very successful career as a physiologist, and whose book is extremely interesting, very impressive. Okay, now, so there is this mystery though. So why did Fisher change his mind, right? When he got out of school, he was sort of sympathetic to the Bayesian position, or didn't see any reason at least to question it. 10 years later, it's not only that he questions it, he's harshly critical. Well, here are some papers on the correlation coefficient. So in 1912, Fisher wrote his first paper on an absolute criterion for fitting frequency curves. Steve Stigler says this is clearly the product of a very bright undergraduate. And in it, basically, Fisher points to the method of maximum likelihood as a way of estimating parameters. And then in 1915, he wrote a very famous paper, Frequency Distribution of the Values of the Correlation Coefficient in Samples from an Indefinitely Large Population. So what he did here was, if you took pairs of bivariate vectors, pairs x, y from a bivariate normal distribution, and you calculated the sample correlation coefficient, what he did was work out the exact distribution of the sample correlation coefficient, something that hadn't been done before. Very impressive, because it's a pretty complicated bivariate distribution. And so he worked out the distribution, but he also had approximations and gave various examples. And then in 1917, Soper et al. So Soper was someone who worked in Karl Pearson's laboratory in London. And so Soper and a bunch of others wrote a so-called cooperative study where they analyzed some of the consequences and applications of what Fisher come up with. And then Fisher wrote a paper in response at some point called, 4 years later, on the probable error of a correlation coefficient deduced from a small sample. So what was the significance of these papers? Well, Karl Pearson was the big name in statistics at that point. He was the Galton Professor of Eugenics at the University College of London. He was the editor of the journal Biometrica. And so he was one of the co-authors of the cooperative study. And he said, Fisher holds that a priori, all values of rho, the correlation coefficient, are equally likely to occur. This raises a number of philosophical points and difficulties. We ask, when are we in absolute ignorance as to rho? Is it according to our experience that all values of the correlation are equally likely to occur? We think that this question must probably, if not certainly, be answered in the negative. So they interpreted Fisher's paper and some of his applications as taking a uniform prior on rho. Now, what Fisher was actually doing was using the method of maximal likelihood, which is equivalent to taking the the posterior median given a uniform prior, but they interpreted it as being a Bayesian result and said, well, the underlying Bayesian prior doesn't really have justification. So it was a criticism of part of Fisher's paper. And here's the famous Karl Pearson. Now, Fisher responded in 1921, and if you read or study Fisher at all, this was not someone who took criticism well. He was a very sort of craggy person. And so he says, Karl Pearson's comments upon my methods imply such a serious misunderstanding of my meaning that a brief reply is necessary. Now, by the way, this is 1921, and the Pearson paper was written in 1917. So you say, why did he wait 4 years to reply? And the answer is he didn't. He wrote a reply, and Pearson refused to publish it. And in fact, he declined to publish several of Fisher's papers over the next several years. And so at some point, he and Fisher completely cut ties. And so Fisher says, from this passage, and he's quoting Pearson, he says, which did not refer to my paper, which had appeared in the previous year and to which the cooperative study was called an appendix, might imagine that I had used Boole's ironical phrase, equal distribution of ignorance, and that I had appealed to Bayes' theorem. I must therefore state that I did neither. And in fact, he was not using Bayes' theorem, he was using maximum likelihood. So now, I think if you're trying to understand sort of the history of mathematical statistics in the first half of the 20th century, the Fisher's disputes with a variety of people were an important element, especially in the 20s and 30s. And this criticism of, and in general, the fact that Pearson rejected papers of his and so on, it still rankled in 1956. So Pearson died, I think, around 1935. And so this is more than 20 years later. And in Statistical Methods for and Scientific Inference, Fisher wrote about Pearson. He said, Pearson's energy was unbounded. In the course of his long life, he gained the devoted service of a number of able assistants, some of whom he did not treat particularly well. He was prolific in magnificent, or grandiose, schemes capable of realization, perhaps by an army of industrious robots responsive to a magical wand. The terrible weakness of his mathematical and scientific work flowed from his incapacity in self-criticism and his unwillingness to admit the possibility that he had anything to learn from others, even in biology, which he knew very little. His mathematics, consequently, though always vigorous, were usually clumsy and often misleading. In controversy, to which he was much addicted, unlike myself, he constantly showed himself to be without a sense of justice. So you don't have to be much of a psychologist to realize that, so this really, it's remarkable that 20 years after Pearson had died, Fisher would write in this vein, and it really showed the real depths of his feeling. And now, part of this stems from the fact that when he didn't get along with Pearson at these early stages, he was very early in his career. The cooperative paper came out in 1917. It was only in 1919 that he went to Rothamsted, and only in the 30s that he went on to a professorship at Cambridge. So in the late teens of the last century, he was not financially or professionally secure. And so, having attacks by someone of Pearson's stature was obviously something he didn't like. But nevertheless, it's sort of interesting. It's sort of hard to think of very many people who write this way 20 years after someone else's death. But it gives you a sense of where he was coming from. Okay, now we'll move on. So this is Fisher. Okay, so he gets into an argument with Pearson, and as part of this argument, he adopts a very stridently anti-Bayesian viewpoint. Now we fast forward another 10 years or so, 1930, inverse probability. So inverse probability is the title of a paper, which was the origin of Fisher's famous fiducial argument. And so the paper starts out with a mandatory attack on the inverse method. Fisher says there are, however, certain cases in which statements in terms of probability can be made with respect to the parameters of the population. So that's what Bayes is trying to do. But he says, yes, actually, there are ways you can do this. Now, if you look at this paper from what I'd call a modern perspective, current day perspective, what he did was he discovered a general method of constructing, I mean, he never used this terminology, but what he basically came up with was a method of constructing confidence intervals in the case of a continuous one parameter family. And so I'll briefly go through the method in a moment. What's interesting is there's almost nothing controversial in this paper. Now, given later on that there was this big dispute between Fisher and Neyman, where Fisher said, well, fiducial inference has nothing to do with confidence intervals, which Neyman then gleefully seized and said, fine, well, therefore, I claim all the credit for developing the theory of confidence intervals. I don't understand what Fisher's doing, but whatever he's doing, he's not doing my confidence intervals. So what I'm doing is novel and original and is due to me. It has nothing to acknowledge with Fisher. And now when I say there's nothing controversial in this paper, a long time ago, Charles Stein at Stanford once told me that with the exception of one sentence in this paper, there was nothing he found objectionable to it. And Stein was sort of on the exact opposite side. He was a very hardcore frequentist of the Neyman school. Very brilliant man. But he said, this particular paper, there's one sentence that I think is off, but otherwise it's just fine. So what did he do? Well, in modern language, here's the setup. You have some kind of continuous statistic T, okay? Theta is going to be some one-dimensional parameter for T. So maybe it's the normal distribution where the variance is known, but you don't know what mu is. Or it might be an exponential distribution where you don't know the exponential parameter. You have some one-dimensional distribution where you have a situation where it's a one-dimensional parameter. Unlike, say, the general normal, you have two parameters, mu and sigma squared. But here you have one parameter, and T sub p of theta will be the so-called pth quantile of T under theta. So what that means is that if you have the statistic, so given theta, T sub p of theta is a number, and what number is it? Well, it's that number such that the probability, if theta is the true parameter, that T is less than that number is equal to P. Okay, so if you give me P, then if theta is the correct parameter and you choose this number, which is a function of theta, then the probability that T is less than the number is equal to P. Okay, and you can do that because of the sort of under appropriate assumptions. So in particular, if you assume that T sub p is strictly increasing in theta, so the bigger the number, the bigger the probability that you fall to its left. Well, if T sub p is strictly increasing, then T sub p inverse is also strictly increasing. So I can hit both sides of this with T sub p inverse, and that converts this into the probability under theta of T sub p inverse less than theta is equal to P. So what this means is for each theta, you see, here's T. This is the statistic you observe. It's a random variable. This T sub p and T sub p inverse, they're actually determinate functions. There's nothing random about them. I mean, they're calculated from random quantities, but T sub p theta is a deterministic function of theta, and T sub p inverse is another deterministic function. So what this is saying is if I hit the random quantity T with this parameter, with this, determinate function, and I ask, what's the probability that it will be less than theta? The answer is it will be equal to P independent of theta. Okay, for each theta, the probability that I'm less than that, if theta is the true parameter, is always going to be P. So what that means is, suppose I observe T and then I calculate this guy here, okay? And then I'll repeat that. I do another trial and I calculate this quantity. It'll be some other number. And I do it a third and fourth and fifth time and so on. So I keep on for successive values of T. I calculate, this is a number I can calculate given T. And suppose I consider the interval from that value to infinity. Well, what the statement is saying is 95% of the time, this interval will contain the true value of theta. So it's a 100p% confidence interval for theta. Okay, and so this is a way of calculating confidence intervals for theta, which is completely general, right? It has all I needed to know was, you add some, regularity condition, that t, this guy was strictly increasing and its inverse, therefore, is strictly increasing. But subject to very mild conditions, this argument gives you is a sort of a machine you can crank to generate confidence intervals. And so that's what Fisher actually discovered. And that's what Stein didn't find objectionable. This was a way of coming up with confidence intervals in the one-dimensional case. Now, Fisher's clearest state, now this then became a source of huge controversy, in part because although there's absolutely zero controversial about what's going on over here, when Fisher tried to extend this to 2 or more parameters, all sorts of problems came in. Basically, there's no obvious single way of doing that. And so there was a lot of controversy. And so if you look at Fisher's correspondence, there's a letter from him to Tukey, because Tukey wrote to Fisher saying, well, I don't really understand certain aspects of this. And so Fisher replied. And so this is in the 50s, this is this attempt to try to make things clear. He says the probability integral of the exact frequency distribution, so that's this thing we were seeing in the last slide, in finite samples of an exhaustive statistic. So later on, when he writes his last book, Statistical Methods in Scientific Inference, he throws in caveats that weren't present before. And because the point is he's trying to give some uniqueness to what's going on. And so he's saying you can't do this for any statistic. It has to be an exhaustive statistic. So what he really means by that is a sufficient statistic. So he says it's used to form a continuum of probability statements of this form. We're using the monotonic properties of the functions. You get this statement, so we've seen that. A complete set of probability statements about theta in terms known for a given sample value t. So what he's now saying is, I actually get a probability distribution on theta. And how do I get that probability distribution? Well, for each value of p, I can calculate this guy here. And if I interweave all of these lower bounds on theta, it gives me a CDF. It gives me a cumulative probability distribution on theta. So he's now viewing the totality of these statements for each value of p. He's using the totality of these as giving, well, they form in a purely mathematical sense, that's not controversial, they form a CDF, but he's viewing that as describing the distribution of our uncertainty about p. So he hints at that in his 1930 paper, and that one sentence hint is what Stein found objectionable. But in the 1950s, he's being very explicit. He's saying, for me, a fiducial distribution it's the totality of these statements which form a distribution in this one-dimensional case on theta. And I'm going to think of that. Now, and so here's a quotation from the 1930 paper, and it's a little dense, but let's just read through it so we get some sense of Fisher in his own words. So he says, if we give to p any particular value such as 0.95, we have a relationship. And so this is just, if you like, in words, what we were seeing before in formulas. We get a relationship between the statistic t and the parameter theta, such that t is the 95% value corresponding to given theta. And this relationship implies the perfectly objective fact. And you see, here's the point. This is why Stein didn't have a problem with it. At this stage, he's talking about things in purely sampling terms. He says the perfectly objective fact that in 5% of samples, t will exceed the 95% value corresponding to any actual value of theta in the population from which it is drawn. To any value of t, there will moreover be a particular value of theta to which it bears this relationship. We may call this the fiducial 5% of theta corresponding to a given t. If usually, if not always happens, t increases with theta for all possible values, we can express the relationship by saying that the true value of theta will be less than the fiducial value, percent value corresponding to the observed value of t in exactly 5 trials of 100. Okay, so the reason I wanted you to see the actual passages, I mean, he's, in several cases, he's making frequency statements as an interpretation of what's going on. And that's why a hardcore frequentist like Stein said, I don't see any problem with this paper, because he's being honest about exactly where the frequency is coming in. It's coming in trials. And he's saying in 5 trials out of 100, we'll have this relationship. And he says we can construct a table. So as soon as you calculate t, what we may know as soon as t is calculated what the fiducial 5% value is, and that the true value of theta will be less than this value in just 5% of trials. Again, a frequency statement. This then is a definite probability statement about the unknown parameter theta, which is true irrespective of any assumption as to its a priori distribution. So I claim if I've inspired you to go back and look at this paper, I mean, he's basically just describing what a confidence interval, but in this special one-dimensional case where he actually has a formula based on the probability interval for calculating things. Okay, now another important difference at this stage is that Bayesian fiducial probabilities can coexist. So later on, Fisher basically said, look, sometimes, very rarely, but sometimes we actually know prior distributions. And then the Bayesian method makes sense, and that's what you do. But if you have no basis for a prior distribution, you can't do Bayes at all, but you can do my fiducial. So he's not, so back in his 1930 paper, he's saying they can coexist. He says the fiducial frequency distribution will in general differ numerically from the inverse probability distribution obtained from any particular hypothesis as to the prior probability. So he's saying you get different answers. Since such a hypothesis may be true, the prior probability, it's obviously, it is obvious that the two distributions must not differ not only numerically, but in their logical meaning. So he's saying if you're doing Bayes, it's because you actually have some reason establishing this prior, right? Maybe you actually have some objective way of generating the parameter, that kind of thing. He's saying we're in a very different situation logically when you don't have that information, but then you can use the fiducial approach. There's no contradiction between the two statements, but he changed his mind about this later and basically said you can have one or the other. But if you have grounds for one, that destroys the grounds for the other. Now, can this be extended to the multi-parameter case? Well, the resulting difficulties are what led to a shift in Fisher's views. So in Neyman's 1934 paper, Neyman, this is a paper that was written on confidence intervals. And it's fascinating to go back to the JRSS and look up this paper because Fisher was one of the discussants, and it's a very polite exchange. Now they disagree on some things, and Fisher raises certain concerns and so on, but it's still very polite. But then in 1935, Neyman gave another paper, and this was a paper on sampling, design of experiments, and he was very critical of, or he criticized something that Fisher was doing in the design of experiments, and Fisher was incensed. And again, it's very instructive to go back and look up these discussions because, so in 1935, the discussion is not polite at all. Fisher is really says, last year, I'm paraphrasing, but this isn't so far off. He says, last year, Neyman gave a paper on something he understood, and it was a very interesting paper. He would have been well advised to stick to things he understood because that's not the case now. And then Neyman waited and composed a very sharp rejoinder, which was then also published. Now, and so at this point,
Sandy,
yes, please.
The quote from, maybe you were going to say, but the quote from Box, when is that supposed to have happened?
Maybe the late 30s. So, because of this dispute that arose between him and Neyman, he was at pains to say, what I'm doing is not confidence intervals. And, fiducial inference is something completely different. And he started then evolving because if it's not confidence intervals, what is it? And he started, his views started. And so at some point, he and Jeffries had this conversation. I think it's the late 30s. It could be potentially in the 40s. But he and Jeffries, although they were philosophical opponents, so part of, they were on very good terms. And so when you look at Fisher's various correspondence, I mean, sometimes, I mean, he's very sharp when he talks to people, and sometimes he's very friendly or very polite. And part of it, I think, has to do, there are a number of things, but one of them is he thought of himself as a scientist, and he thought a lot of the bad statistics from his perspective was arising from mathematicians who really didn't understand how science worked. And so Harold Jeffreys was a distinguished geophysicist and Cambridge man too, and Fisher had a lot of respect for him. So even though they clashed in print, in person they were actually in quite good terms. And so he had this conversation with Jeffreys one day where he said he agreed with what Jeffreys was doing much more than Neyman, and Jeffreys said, yeah, we are closer in our approach. Because both of them eventually they were involved in inference, degree of belief, as opposed to a frequentist interpretation. And so this evolution is evident in Fisher's last book, Statistical Methods in Scientific Inference, where he's at pains to try to emphasize the difference between him and the frequency school. And here's a picture of Sir Harold Jeffreys, who was at St. John's, which is just the street from. So Fisher was at Keys. And so if you're familiar with Cambridge, St. John's is a bit up the way. Okay, so that's two parts of the talk so far. So one thing I've discussed is Fisher's initial views, then this change that came about because, so part of this is what's going on is that Fisher was not a philosopher in the sense of being a very careful conceptual person. He had fantastic intuition, and he was great with concrete examples and coming up with extraordinarily clever methods for how to deal with them. But he was never a sort of a deep philosophical conceptual person, in my opinion. And so it was a struggle for him because people were saying, I don't understand this fiducial inference stuff. And he found it very difficult to explain this to other people. If you go back to his collected papers, there's this fascinating correspondence between him and fray, who was a probabilist and statistician in Paris. And fray was a very distinguished older character, and Fisher had a lot of respect for him, even though he was a mathematician. And so in this fascinating correspondence, fray very politely says, well, you say thus and such in your paper, and I don't understand that. And could you clarify it? Fisher writes this very polite letter explaining. And then fray writes back and says, thank you, but in your reply, there's this sentence, and I don't understand what that means. Now, when it's the case of Tukey, Fisher could be extremely negative. So if you look at the correspondence and look at the letters with Tukey, at this point, Tukey would write something like that back, and Fisher would say, you're learning, but you're only learning very slowly. If you could only get it through your thick head. And I'm actually not exaggerating the language, but he didn't do that with fray. He was, fray was this older, very distinguished person. And so he's very polite in his answer, but fray is very persistent. And then he writes another letter, third letter, where he says, well, I thank you for that. That clarifies some things, but I still don't get. And I think there may be a total of 6 back and forths in which Fisher is constantly polite. But in each case, what fray is saying, well, this sentence doesn't really sort of make sense to me. What's your justification for saying that? So, but Fisher did struggle, and one way of thinking about this statistical methods for research for scientific inference book in 1956 is it's his supreme attempt to try to explain things in as clear a way as he can. He's trying to nail down to the best of his ability conceptually what he means, what are the conceptual foundations. And so at this point, the nexus between him and Bayes becomes quite interesting. So he's actually an admirer of Bayes. And so in SMSI, this 1956 book, he writes, and so this is Bayes' famous posthumous paper, right? An essay towards solving a problem in the doctrine of chances, which was published a couple of years after his death in 1763. And Fisher says of this, in mathematical teaching, the mistake is often made of overlooking the fact that Bayes obtained his probabilities a priori by an appropriate experiment, and that he specifically rejected the alternative, introducing them axiomatically on the ground that this might not be perhaps looked at by all as reasonable. Moreover, he did not wish to take into his mathematical reasoning anything that might admit dispute. So Fisher is saying, I'm looking at Bayes' paper and I think it's actually quite good. And so here's the first page, right? An essay towards solving a problem. Now, thanks, of course, to JSTOR, we will access this instantaneously for free. An essay towards, and was republished, I forget, in the 50s or 60s with a commentary by, I think, George Barnard in Biometrica. So there's a sort of modernized version by the late Reverend Mr. Bayes, FRS, communicated by Mr. Price. So this is the famous Price in a letter to this was, I think, the Secretary of the Royal Society. Read December 23rd, 1763. I send you an essay which I found among the papers of our deceased friend, Mr. Bayes. Okay, so what was this procedure that Fisher thought was good? Well, instead of positing a uniform prior, what Bayes did was he posited a physical mechanism. And his procedure was to pick out a point uniformly on a table. So it's a famous billiard table. You project that onto the horizontal axis. Okay, so just imagine if this is the table, the billiard ball is somewhere on the table, and then you project downward onto the horizontal axis. The position of this point is uniformly distributed because the idea is the position on the table is uniform, so therefore the projection is uniform. And then you record subsequently if other points W on the axis lie to the left of O. Okay, and then it's not hard to show, or see, I'll get back to that, that if you follow this procedure where so there are two things. Number one is once and only once you pick a point and project. Okay, and then in subsequent trials, you're looking at different things and saying, are they to the left of a zero or not? And that's what a success or failure is. And so this it generates a sequence of independent trials having a probability P of success where P is uniformly distributed on 0, 1. So what Bayes is doing is he's generating a uniform prior on P by this physical mechanism. And for some reason, I tried to fix this, but it's flipped, unfortunately. But this is Bayes' billiard table. It's from the paper, but it's flipped. I was trying to master how to. There's some extra R package you can download to flip this, but I didn't have time to do that. But the idea is you can see the projections. The idea is here's the table, but you're projecting down. So what are some, then you can figure out some mathematical consequences of this. So if Sn counts up the number of successes, the number of times you get a 1 versus a 0, then the probability that the sum is equal to any particular value between 0 and n is uniform, discrete uniform, 1 over n plus 1 over n plus 1. If you say what's the posterior for P given a successes out of n, it's given by the binomial. If you say what's the probability that having had a successes out of n, you'll have a success in the next trial, it's a plus 1 over n plus 2, which is Laplace's famous rule of succession. But you could also do something predictive and say, I observe A successes and B failures. What's the probability that in the next C plus D trials, I'll get C successes and D failures? And it's given by this. You just work, you do the math, as they say, and you just get this expression for the predictive distribution. Okay? All very simple mathematics, very simple standard mathematics. So, now, at some point, now Pearson was very interested in history too, and so at some point he read Bayes' paper too, and at some point he posed a question. He said, what he called the fundamental problem of practical statistics. An event has occurred A times out of A plus B equals n trials, where we have no a priori knowledge of the frequency of the event. What is the probability of its occurring C times in a further C plus D trials? So he says that's the fundamental problem of practical statistics. So if you like, this he's saying the most important problem of statistics would be what we describe as discrete predictive inference. Okay, I observe a discrete number of outcomes, and I'm now trying to predict a discrete number of outcomes. Okay, but this answer depends, of course, on the assumption of the uniform prior P, P, and so this is Fisher criticized it, and Pearson, others did as well, and so Pearson realized, in fact, Pearson was criticizing Fisher in 1917 for having assumed what he thought was an assumption of a uniform prior. So this is a problem for Pearson. How do you get around the answer to the fundamental problem? This depends on this assumption that seems hard to defend. So Pearson had an insight, sort of. He says in 1920, it has occurred to me that possibly the bull itself is a chimera, and there may be no need whatsoever to master it. In short, is it not possible that any continuous distribution of a priori chances would lead us equally well to the Bayes-Laplace result? If this be so, then the main line of attack of its critics fails. So Pearson says, gee, wouldn't it be great if this predictive probability that we saw earlier, CD in terms of AB, wouldn't it be great that even though the standard derivation uses the uniform prior, wouldn't it be great actually if it depended, it was the same for any distribution, continuous distribution in P? He says, thus it would appear that the fundamental formula of Laplace in no way depends on the equal distribution of ignorance. It's sufficient to assume any distribution, which may vary from one type of prior probability to another. So Edgeworth, who's still alive in 1921, wrote a paper saying, no, you're wrong. And then a few years later, Burnside, who's much more famous in group theory, right, for Burnside's theorem, said, no, you're wrong. And in fact, it's just obvious that Pearson's assertion is clearly absurd, right? I mean, you can just do concrete examples where you give P a non-uniform distribution and you work out the predictive probability and just changes, right? So it's a remarkable gaffe on Pearson's part. But eventually he was, although slowly, was persuaded that he was wrong. But he must have discovered something, right? And what he actually discovered is, suppose X is the position of that initial point O, okay? Well, what's the probability of a success then? So X is, that's this cap X. So suppose I observe that cap X is little x. Well, a success is, and let fx be the CDF of this guy, okay? It's the probability that in subsequent trials, the random variable will be less than or equal to X. And it's a very simple fact in mathematical probability that F is continuous, but not necessarily the uniform. But if you look at F of X, it is uniform. So if you haven't seen that before, let me just back up and say, okay, you have this Bayes process where you pick a point at random, that's the O, and then from this, with some distribution, capital F. And then you repeat this process over and over with the same distribution. And you say, are subsequent balls to the left or right of the first one? And if they're to the left, that's a success. If they're to the right, that's a failure. But I'm using the same distribution both to pick the initial O and the subsequent ones. Okay, and let F be the CDF for this process. Then, given you observe a value of X, what's the probability of the success in the future? It's F of X. It's the CDF applied to the observed value of X. And the point is, if instead of viewing X as a single value that I observe once, if I think of it as random quantity, then F of X is random too. So that's the random mechanism by which you're generating probabilities. And it's a simple calculation to show that that's uniform. Okay, so the point is the distribution of P is still uniform. Okay, but the point is, are things going crazy? No, because the point is the location X, the mechanism for generating P, doesn't have to be uniform. But whatever that continuous distribution for generating the X is, the resulting generation for distribution for P is uniform. Okay, so that's what Pearson actually discovered. So in other words, you could have a very non-uniform distribution of where the billiard ball lands on the table, and then when you project onto the horizontal axis, a very non-uniform but continuous distribution of where the ball falls. But if the substance you fall to the left or right is the criterion for success or failure, then the probability of success or failure generated by this mechanism is uniform. That's what Pearson actually discovered. Not that the answer doesn't depend on the uniform distribution of P, but that in this physical mechanism that Bayes came up with, okay, the physical mechanism doesn't have to be uniformly distributed. Okay, and he eventually understood this difference with help. And so in a later paper, he wrote, I owe to Miss Ethel Newbold this insight into the exact relation between the two hypotheses. Now, of course, he couldn't quite bring himself to say I was completely wrong. He tries to argue that this is really what he meant, but it's difficult at his age to admit mistakes. Okay, so this was Pearson's discovery. Now, Fisher actually used this example in this 1956 book, Statistical Methods for Scientific Inference, okay? And he used the example of radioactive decay, okay? And so he considers zeta to be a multiple of an earlier observation. So, there's a lot of interesting things in this, despite its polemic nature and so on. There, just in terms of the math and the examples, there's a lot of interesting stuff in it. And so the idea is, imagine that X is generated in some fashion, and you multiply it by C, and that's going to be the zeta guy. And he considers this to be, okay. So the idea is the initial observation is X, and the later observation, zeta, are C times X. Now, if you set C equal to 1, then the initial observation, in other words, it's when do you have a radioactive decay? And then you're asking subsequently, do later decays occur before or after that? Okay, so that's exactly what Bayes is doing. But here, since radioactive decay is exponential, it's clearly not uniform. And Fisher points to this as basically as what Bayes was doing. And he says, in many continental countries, this distinction, which Bayes made perfectly clear, has been overlooked. And the axiomatic approach which he rejected has actually been taught as Bayes' method. The example of this section exhibits Bayes' own method, replacing the billiard table by a radioactive source as an apparatus more suitable for the 20th century. Okay, but this is, but he doesn't mention Pearson, but he's basically using this example, which is basically what ultimately Pearson had in mind. Now, there are some other, so I'm going to, let's see, let me just check on time for the moment. So how am I doing on time? 4:30, so I've used up about an hour. So what I'm going to do is try to wrap up in about 10 minutes tops, okay? And then we can break or not and answer questions and so on. So what I'd like to argue is if you go through this book and overlook all the polemics and stuff like that, I mean, there are a number of interesting ideas, but also another interesting conundrums. There's this rule of succession. And and Venn is famous for criticizing it, right? The rule of succession that goes back to Laplace, and Venn criticizes it. And surprisingly, in Fisher's book, he criticizes Venn. He has a historical chapter early on, and he says, Venn's arguments are surprisingly weak, and so initially when I saw this is sort of puzzling, right? So Fisher's this very political, if you like, polemical person. Then he views as on the side of the angels in terms of his view of what probability is and isn't, and yet he's willing to criticize Venn. And the question is, why is he criticizing Venn if N is an ally? And the answer is because later on, he talks about posterior means of P using 3 different approaches, and one is his fiducial approach. So-called, now I say fiducial approximation because if you get into the nitty-gritty of what's going on, when the observations aren't continuous but discrete, Fisher, there's no corresponding continuous, there's nothing analogous to what Fisher did continuously, but you can approximate it, the continuous case. And so if you carry that method out as he does, here is the posterior mean of P using the fiducial approach, but it's an approximation since you're not in the continuous realm. And then suppose you have the flat prior, okay? So here's a plus 1 over n plus 2, and you can expand it out this way. Okay. And you can see that they agree in the lead term, but they differ in the second term. And then his friend Harold Jeffreys had this other prior, 1 over pi root p q d p. And if you do that, it's a plus a half over n plus 1. And that's, the lead term is the same. And actually, the second term agrees, interestingly, with the fiducial approach. And it's only the third term over here that disagrees with the fiducial approach. Okay, and he says, to this extent, a particular given distribution a priori may be nearly equivalent to complete ignorance a priori. So what he's saying is, even though I don't think of the flat prior as being right, nevertheless, it's giving an answer that's quite close to the right answer, which is the fiducial approach. So the point being, he can't let this attack by Venn go unanswered, because if you accepted Venn's criticisms, they would be criticisms not only, if you accepted Venn's qualitative criticisms, you would be accepting criticisms not only of the classical flat prior, but you'd also, in principle, be accepting a criticism of the fiducial approach as well. So he doesn't say that, but that's obviously his motivation in disagreeing with Venn. And here's a picture of the great John Venn. And I don't know that we have a date as to when this was taken. Now it says John Venn, SD, so this would have been, well after he graduated initially. And I can't resist. This is a picture. I have a friend, Anthony Edwards, who now retired, who's was fellow and then professor at Cambridge, in Keys, actually, the same college as Fisher. And now, Cambridge has this interesting thing that if in your institution or my institution, we had John Venn as a former member of the faculty, then his picture would be prominently displayed somewhere in the university, right? But this is Cambridge. And, there are, a gazillion famous past fellows of Keys. And so this picture was languishing somewhere in the basement of Keys. And so Anthony persuaded the college to let him put it up in his office, where it now happily lives. And if you look over, by the way, to the left, you can see that posed picture of Fisher that we saw earlier. So that's Venn. And now I'm going to very quickly touch on a couple of other items, but these are more teasers to get you to it, because it's over an hour, so it's time to wrap up. So these are teasers to get you to go back to this book and look at some of the examples that Fisher discusses. So he talks about Bayesian prediction, a conundrum. So the idea is to try to understand what's going on. He says that this factor in the expression developed above. So that was this idea that I'm going to, see, it's very sensitive. I'm going to try to predict C and D from A and B using a uniform prior. If you go back, look at that expression, you see there's this factor C plus D factorial over C factorial D factorial. And he says it stands only for the binomial coefficients forming the last line or base of Fermat's arithmetical triangle. But he says, so these are these sort of quirky facts he sometimes notices. He says, if I look at the sum, C goes from 0 to C plus D of this factor times P to the C, Q to the D, then of course this adds up to 1. But he says this isn't the only polynomial in PQ, the value of which is constantly equal to unity. I can find other coefficients that do the job too. And so he gives this figure in his book, the arithmetical triangle extended. I'll go back to it in a moment. And he says, if you extend the triangle to any chosen boundary, as for example on the diagram, with 13 totals outside the boundaries, boundary are the coefficients omega CD of a polynomial. So in other words, instead of the other coefficients, when I look at this diagram, I can read off omega of C and D, and I can create this polynomial here. And this too will be equal to 1 for all values of P. And he says we can then use that based on a previous experience of A successes out of A plus B. We can infer the probability of reaching the terminal value CD to be equal to, and then he gives this expression, but now you replace the last guy by omega of C and D. So I'll just briefly explain the way I understand it, but I encourage people to go and look back. The idea is, so here's the arithmetical triangle, right? 1, and then the next line 1 and 2, and 1 and 1, and then the next line you have 1, 2, 1, the next line 1, 3, 3, 1. But the idea is he's drawn this boundary. And so imagine if you're here, you can take a step to the left or a step to the right. So if you take a step to the left, that would correspond to getting a tail, say. If you take a step to the right, that would correspond to getting a head, okay? And if you take, so what we're getting over here is, and the next one is if you take 2 steps, then you can have 2 heads in one way, or 2 tails in one way, or a head and a tail, and that can happen one of 2 ways, and similarly over here. But the idea of this boundary is, imagine that we stop the process when we step outside, okay? So you can imagine I have 1 tail, 2 tails, 3 tails, 4 tails, and then I step outside. Well, doing this, that can only happen in one way.
Hi.
Okay. Sorry, question? So this can only happen in one way. Okay. Now, over here, so this can happen actually only in one way too. Well, 4 ways, sorry. 4 ways, because the idea is I'm going down, but at some point I have to go 1 over. So I can go over, 1 over here, 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 or here. But once I'm here, if I'm to get to here, I have no choice. I have to head down. So there are 4 ways of getting here. Similarly, if I'm at this point and I step to the left as opposed to the right, if there are 18 ways of getting to this square, I go here, and then I've just exited the boundary, so the process stops. So there are 18 ways, and the idea is you get these other numbers by filling things in. Okay, so over here, if I'm at here and I step to the left, there are 52 ways, of getting here, and only 1 way here. But if I'm here, I can imagine going down here, and if I exit over, see, if I'm at 412, there are 2 possibilities, okay? I can either step to the left, and there are 412s of doing that, or I can go over here, okay, to exit the boundary. And there are 824 because there's 412 to the right and 412 to the left. Clear? So if you draw, so you take the sort of standard arithmetical triangle, but then you draw this arbitrary boundary, and it's basically a stopping time kind of thing. You announce the process stops when I exit the boundary. And what you're doing then is saying, well, here are the different possible ways I can stop, right? And I'm counting up the number of ways I can stop. And then the point is the total probability I stop is 1, because if I'm taking more and more steps, at some point I have to step out of the boundary. But there are just limits as to how I can do that. And so if you count up the different number of ways I can step out the boundary and add up their probabilities, that has to add up to 1. And so that gives you this polynomial in P and Q, but with a different set of coefficients that are tied to the boundary. So that's one little thing he throws out. And then right, this is the thing, we read through that already. Right, he's saying, so here's another polynomial, but the 1, 4, and 18 are coming from this diagram over here, 1, 4, 18, and so on. These are the different possible values. So it's an interesting development of a interesting way of thinking about the arithmetical triangle in terms of actually boundary stopping probabilities. And predictive inference for given boundary stopping. He also has something called predictive fiducial prediction, which I'm not going to go into, but this slide simply summarizes this. The idea is you have xi is the sum of ni independent exponentials. And if you say, what is the distribution? It's essentially chi-square on 2n degrees of freedom. And then he says that the fiducial distribution of x given theta is gamma. So it has this distribution. And then he says the fiducial predictive distribution of x2 given x1 has this density over here. So it's an interesting exercise to try to derive this, the mathematics of what he's doing. I'll say one, and I think this is basically my last slide. I'll make some comment about verifiability. He said, so this is part of the frustration though of reading this book. He says it should be observed that such fiducial probability statements about future observations are verifiable by subsequent observations to any degree of precision required. For verification, the original prediction must be held firmly in view. And he says, a somewhat unnatural aptitude for a worker whose main preoccupation is to improve his ideas. It's perhaps for this reason that some teachers assert that statements of fiducial probability can't be tested by observation. Well, but you can't test fiducial probabilities by observation. I mean, because they're not defined in observational terms, right? When you make a confident statement, you're saying that in some, the frequency of successes in a set of trials is thus and such, but that's not what's going on in Fisher's fiducial argument, okay? And so he has this interesting statement, and I really have to write maybe Art Dempster this question, but I don't understand what he means by saying fiducial probabilities are verifiable. But you shouldn't either, because at some point, John Tukey in the 50s wrote Fisher a letter where he said, I don't understand, what do you mean that fiducial probabilities are verifiable by observation? And Fisher almost in his letter basically says, look, here's the probability distribution. And so if you're sampling from that distribution, you'll see, you will verify the probabilities. Well, that's sort of just tautological, right? If you're sampling from an exponential distribution, you'll verify the exponential the probabilities are exponential, but that's not really saying something. What he's seeming to suggest here is somehow my fiducial distribution probabilities will correspond to something that you can actually verify. And to me, at least, I don't see any way of justifying that. And so this is, I think, the final slide. It's another little tidbit. So suppose theta is given the Jeffreys prior. Then there are these interesting situations that some of Fisher's fiducial distributions correspond to Jeffreys priors. So this is part of the reason you see Fisher and Jeffreys said they basically agreed with each other, was largely, were closer, was that at some point you could reproduce some of Fisher's fiducial probabilities as being posteriors with a prior that Jeffreys came up with. However, much earlier, Fisher rejected the use of the improper Jeffreys prior with, I think, good reason. As eventually Dennis Lindley, who used improper priors initially at some point because of some paradoxes that people pointed out. I was at a conference many years ago where he said, you should throw away my book because I wrote a book and it uses improper priors, and I now recognize that it's all nonsense. But the Jeffreys prior is a perfectly, that's fine. That's a proper prior. Well, it's at least I shouldn't say it's proper prior, but it's it doesn't suffer from those paradoxes. Okay. So I believe that's it. So Glenn, do we take a break at this point, or people just pile in with questions, or what?